You're driving an electric car on a busy highway. Your battery is running low, but instead of searching for a charger, something unexpected happens. The car next to you silently begins transferring energy. No cables, no plugs, no stopping. High voltage. This isn't science fiction anymore. According to recent demonstrations and emerging research, wireless energy sharing between electric vehicles is moving from theory into serious experimentation. And at the center of the conversation is Maxwell's latest breakthrough, a system designed to let EVs share power dynamically, safely, and intelligently. But before the hype takes over, let's slow this down, because the real story is far more interesting than flashy headlines. For years, the biggest limitation of electric vehicles hasn't been motors, software, or speed. It's been energy distribution. Charging stations create bottlenecks. Batteries degrade. Infrastructure struggles to keep pace with adoption. Maxwell's new approach doesn't try to solve this with bigger batteries. It asks a different question. What if energy could move, instead of cars having to stop for it? The concept is elegant. Vehicles equipped with compatible systems form short-range energy links using controlled electromagnetic fields. When two EVs are close, at low speed, in traffic, or parked, energy can be transferred wirelessly from one vehicle to another, guided by software that manages safety, efficiency, and limits. No sparks. No exposed connectors. No direct physical contact. Early tests focus on balancing, not miracles. One car doesn't drain another. Instead, energy is shared within predefined thresholds, enough to stabilize battery levels, extend range, or prevent shutdowns in critical moments. And that distinction matters, because this isn't about infinite power. It's about resilience. Engineers involved in similar systems describe it as distributed energy logic, a networked approach where vehicles act less like isolated machines and more like nodes in a mobile energy ecosystem. Think about the implications. During traffic congestion, energy doesn't sit idle in fully charged cars. During emergencies, EVs can assist each other without external infrastructure. In remote areas, fleets can rebalance power intelligently. Suddenly, range anxiety looks very different. Of course, the challenges are serious. Wireless energy transfer must be efficient enough to be practical. Heat management is critical. Interference must be controlled. Safety standards must be airtight. And everything must work seamlessly across different vehicles and conditions. Skeptics are right to question it. But here's what makes this moment important. Wireless power sharing isn't appearing out of nowhere. The underlying science, inductive coupling, resonant transfer, adaptive field control, has already been proven in smaller systems. What's new is scaling it intelligently for moving vehicles. And that's where Maxwell's work enters the spotlight. Rather than brute force energy transfer, the system emphasizes precision. Power flows adjust in real time. Transfer only occurs under safe alignment. Software mediates every exchange. In other words, the system decides when not to share just as carefully as when to do so. That design philosophy signals something deeper. The future of EVs may not be about charging faster. It may be about sharing smarter. And once vehicles become capable of exchanging energy with each other, the entire idea of infrastructure begins to shift. But this story isn't finished. Because the real question isn't whether wireless EV energy sharing can work in controlled tests. No longer is each car an isolated island of charge. Instead, every vehicle on the road becomes part of a living network, constantly negotiating, adapting, and optimizing energy flow in real time. Software algorithms decide when to give, when to receive, and when to conserve. The system prioritizes safety first, efficiency second, and availability third. This is where Maxwell's approach becomes especially interesting. Rather than treating wireless power sharing as an emergency-only feature, the concept treats it as a background capability, something that runs quietly, invisibly, and intelligently. Much like modern cars already exchange data, location, and traffic information, they could one day exchange energy just as seamlessly. Imagine a city commute. Some cars start the day with excess charge. Others don't. As traffic slows, brief, Controlled energy transfers occur. Nobody notices. Nobody intervenes. Yet by the time vehicles reach their destinations, overall energy distribution across the fleet is more balanced than when the journey began. This doesn't eliminate charging stations, but it reduces dependence on them. And that has massive implications. Grid strain during peak hours could be reduced. Emergency response vehicles could stay operational longer without stopping. Ride-sharing fleets could self-balance energy throughout the day. Even rural or underdeveloped regions could gain resilience without massive infrastructure upgrades. Of course, none of this happens without strict boundaries. Maxwell's system is designed with layered safeguards. Power levels are capped. Transfer distances are limited. Continuous monitoring detects anomalies instantly. If conditions aren't perfect, the system simply refuses to engage. No drama. No risk. Because in energy systems, restraint is as important as capability. Testing so far focuses on low-speed scenarios, traffic congestion, parking structures, controlled environments. Engineers want to understand interference patterns, thermal behavior, and long-term component health before pushing limits. This is careful development, not reckless experimentation. And that careful pace is intentional. Because the moment wireless energy sharing becomes reliable, the conversation shifts yet again. People stop asking, "Is this possible?" and start asking, "How do we regulate it? Who decides when a car can share energy? How is consent managed? How are priorities assigned in emergencies? How is fairness ensured?" These are not technical problems alone, they're societal ones. Which is why this technology, if it matures, won't just reshape vehicles. It will reshape how we think about ownership, cooperation, and shared responsibility on the road. And that leads to a future that looks very different from today's EV landscape. A future where energy doesn't just flow from the grid to the car, but between cars themselves. As that future comes into focus, another layer of complexity begins to emerge, one that goes beyond technology and into human behavior. Because once cars can share energy, every journey becomes part of a larger system. A driver with surplus charge is no longer just a consumer. They're a contributor, a moving reserve. And that changes incentives, dynamic credits, priority access, cooperative routing. Energy sharing becomes not just a feature, but a language vehicles use to negotiate the road together. Maxwell's concept anticipates this. Instead of random or forced transfers, the system is designed around intent and context. Vehicles communicate anonymously, assessing needs without revealing identity. A car low on charge near a hospital gets priority. A fleet vehicle nearing the end of a shift can give without risk. Everything happens within guardrails, ethical, technical, and legal. And this is where the skeptics pause. Because the idea isn't naive. It doesn't assume perfect cooperation. It assumes managed cooperation, guided by rules, software, and constant verification. Much like air traffic systems manage thousands of flights without chaos, this approach treats energy as a managed shared resource, not a free-for-all. At the hardware level, engineers refine efficiency. Transfer coils are redesigned to minimize losses. Shielding improves. Alignment tolerance increases. Each improvement may seem incremental, but together, they close the gap between lab feasibility and road readiness. Nothing here happens overnight, but momentum builds. Pilot programs expand quietly. Controlled fleets. Closed campuses. Industrial parks. Places where variables can be measured, mistakes contained, and lessons learned. Data accumulates. Models improve. Confidence grows, not from promises, but from patterns. And then comes the moment every disruptive idea faces. The question of scale. Because one city experimenting is interesting. 10 cities are significant. But global adoption forces a reckoning. Standards must emerge. Compatibility matters. Manufacturers must agree on protocols or risk fragmentation. Regulators step in. Insurance companies ask hard questions. Lawyers read between the lines. This is where many ideas stall. But if wireless energy sharing survives this phase, it means something important. It has crossed from innovation into infrastructure. Not cables in the ground, but intelligence in motion. And once energy becomes mobile, cooperative, and adaptive, the EV conversation changes forever. Charging stops being an event. Range stops being anxiety. And energy stops being something you hoard. It becomes something you manage together. And that raises a final, unsettling idea, one that reframes everything we think we know about transportation. What if the smartest car of the future isn't the fastest or the most expensive, but the one that knows when to give, when to take, and when to wait? Because if that's the case, then wireless energy sharing isn't just a feature. Because trust is what allows systems to operate without constant human intervention. It's what lets planes fly themselves, power grids stabilize automatically, and data move freely across the globe. And in Maxwell's vision, trust becomes the foundation that allows vehicles to share something as critical as energy. At this stage, the discussion isn't about coils or software anymore. It's about confidence. Confidence that the system won't overreach. Confidence that safety overrides convenience. Confidence that no single vehicle can exploit the network. That's why transparency becomes central. Every energy exchange is logged, auditable, reversible. Drivers don't have to understand the physics, but they need to understand the rules. Clear limits, clear benefits, clear protections. Without that clarity, no technology, no matter how advanced, earns long-term acceptance. And this is where the breakthrough matures. Because true innovation isn't just about what's possible, it's about what people are willing to live with. As designers refine the system, they begin building in opt-out principles, fairness constraints, and local control. A car can share, but only within comfort zones set by its owner. A fleet can prioritize, but only under agreed conditions. The machine adapts to human values, not the other way around. That design choice may be the most important of all, because it signals a shift away from domination toward cooperation, not just between vehicles, but between humans and the systems they rely on. At this point, the question changes yet again. It's no longer, can cars share energy wirelessly? It becomes, what kind of society do we build when they can? A society that treats energy as a rigid commodity, or one that treats it as a flexible, shared resource? A society that optimizes only for individuals, or one that allows collective stability to emerge naturally? Those answers won't be written in code alone. They'll be shaped by policy, culture, and public trust. But one thing is already clear. If Maxwell's wireless energy sharing technology continues along this path, measured, cautious, and human-centered, it won't just change electric cars. It will quietly redefine how we think about movement, cooperation, and responsibility in a connected world. And the road ahead isn't about speed. And as direction becomes the focus, something unexpected happens. The technology stops feeling futuristic and starts feeling inevitable. Because once people understand the logic behind wireless energy sharing, it no longer sounds radical. It sounds practical, almost obvious. Just as data flows through networks without us thinking about the routers and protocols, energy too begins to feel like something that should move intelligently, where it's needed, when it's needed. Engineers begin framing it differently. They stop calling it wireless charging. They call it energy orchestration. Cars are no longer passive storage units waiting to be filled. They become active participants, constantly negotiating supply and demand in the background. A vehicle doesn't ask, how much energy do I have? It asks, how much energy does the system need right now? That shift alone changes design priorities across the entire industry. Battery health becomes central. Software reliability becomes critical. Predictive modeling replaces reactive charging. Vehicles begin to plan not just routes, but energy roles, when to conserve, when to contribute, and when to rely on the network. Maxwell's work hints at this future, without overstating it. There's no promise of eliminating the grid, no claim of endless power. Instead, there's a quiet insistence on efficiency, cooperation, and intelligent limits. The system works best not when everyone takes, but when everyone participates responsibly. And that idea spreads. Urban planners start paying attention. Fleet operators run simulations. Energy economists begin asking new questions. What happens to peak demand when energy flows between moving vehicles? How does shared mobility affect long-term battery life cycles? Can cooperative energy systems reduce total infrastructure costs? None of these questions have final answers yet. But for the first time, they're being asked seriously. And then comes a subtle but powerful realization. Wireless energy sharing isn't competing with existing solutions. It complements them. Fast chargers still matter. The grid still matters. Renewables still matter. But layered on top of all that is intelligence, an adaptive layer that reduces stress, smooths extremes, and adds resilience where none existed before. And resilience, as history has shown us, is what separates good systems from lasting ones. At this point in the journey, it's impossible to say exactly how far this technology will go or how quickly it will mature. But it has already crossed a threshold, from novelty to necessity, from question to conversation. Because once people see that cooperation can be engineered, they begin to expect it. What once sounded experimental now feels like an evolution, one more step in a long line of systems becoming smarter, quieter, and more interconnected. People no longer ask why cars would share energy. They start asking why they wouldn't. Because the benefits compound. Traffic becomes more forgiving. Emergencies become more manageable. Energy becomes less brittle. A stalled EV on the roadside stops being a crisis. A nearby vehicle can stabilize it long enough to reach safety. A delivery fleet doesn't lose hours to charging gaps. It redistributes internally. A city under strain doesn't collapse into chaos, it flexes. And through all of this, the technology stays mostly invisible. No dramatic moments. No flashing alerts. Just systems doing what they were designed to do, quietly optimizing in the background. That invisibility is the final test of maturity. When drivers stop thinking about the feature. When planners stop advertising it as new. When it becomes expected behavior. That's when it has truly arrived. Maxwell's latest breakthrough, if it continues on this path, won't be remembered for its first demonstrations or early headlines. It will be remembered for normalizing a different idea. That energy doesn't have to be hoarded. That mobility doesn't have to be isolated. That technology can reward cooperation without forcing it. And in a world facing growing pressure on grids, cities, and resources, that idea carries weight far beyond electric cars. Because once energy can move intelligently between machines, the question naturally extends outward. What else could share? What else could balance itself? What else could become resilient instead of fragile? Those questions don't end at the road. They're only just beginning. And that is where this story comes to rest. Not with a dramatic promise. Not with a bold prediction. But with a clear shift in how we imagine the future. Maxwell's wireless energy sharing concept doesn't ask us to believe in miracles. It asks us to believe in intelligence, applied carefully, cooperatively, and with restraint. It suggests a world where cars don't just move people, but support one another. Where energy isn't trapped in silos, but guided where it's needed most. If this technology succeeds, it won't do so because it was revolutionary. It will succeed because it was reasonable. Because it solved real problems quietly. Because it respected limits. Because it earned trust. And in the end, that may be its greatest breakthrough of all. Not wireless power. Not shared batteries. But a future where innovation isn't about taking more,